Hello everyone, my name is Arnold Fernandes. I'm a PhD student at Missouri University of Science and Technology. My advisor is Dr. Rui Bo. My poster is titled Distributed Dynamic State Estimation in Power System Under Cyber Attacks. With the increasing use of phasor measurement units, the dynamic state estimator can be utilized in power system. Dynamic state estimators can incorporate physical model. This makes it robust to simple attacks. A distributed state estimation framework is pursued here. It is advantageous as it reduces long-distance communication, eliminates the need for a centralized state estimation algorithm, and allows for parallel computation. A distributed power system can be shown in Figure 1, where the distributed control centers obtain measurements from various points of the power system via a network. It's possible that attackers could manipulate the measurements that are going through this network. Here we will consider the 8-bus 5-generator system-based power system. Each generator has a nonlinear dynamical model and algebraic equations which interconnect the generators. Now this model is nonlinear in nature and so it has to be linearized. A linear model is obtained in equation 3, which is further discretized and equation 4 is obtained. Here we can see that here we have a state equation and a measurement equation. We also have noise in the process and noise in the measurement. Now, to overcome this noise, we use a Kalman filter. A Kalman filter gives us a good value of the true measurement, and it also helps us get the value of unmeasurable states. Since we are working towards a distributed framework, we have utilized a distributed Kalman filter in our project. A distributed Kalman filter is a state estimator, and you can assume a distributed Kalman filter at each of the distributed control centers. This distributed Kalman filter takes in local data from the power system, and it also communicates with its neighboring Kalman filters on communicates its estimates with the neighboring Kalman filters, and it tries to come up with a good estimate of the states of the power system. To detect attacks in such a system, normally a chi-square detector is utilized. A chi-square detector computes a quantity based on the error between the measurement and the estimate, and it tries to compare it with the scalar quantity. If the value is above the scalar quantity, then an attack has occurred in our system. If not, then there is no attack. Simulation result for the healthy case. Here we see figures A and B are the delta and the omega of the generators. Here you can see that the solid lines show the states and the dashed lines show the estimates. You can see the solid lines and the dashed lines overlapping each other, which show that we have a very good estimate of our states in the healthy case. Here we have a detector that gives a value of 0 if there is an attack, if there is no attack, and gives 1 in case of an attack. Currently, since we are in the healthy case, we get a 0 value. Moving on to the attack case, we see that in the case that the attacks, in the case the measurements are attacked, so currently delta 4 and omega 4 measurements have been targeted at control center 2, and we can see that there are spikes in the estimate. So the estimate delta 4 hat and omega 4 hat are not good because of the presence of attacks. Furthermore, we see that the chi-square value shows that an attack has occurred at control center 2. Summary and conclusion. A dynamic linearized model of the power system was obtained. This model was then utilized in the distributed Kalman filter framework. A chi-square detector was also used to check if the measurements have noise or attack in it. Once the attack is detected, a mitigation technique can be designed such as the Bayesian learning. Thank you everyone for paying attention to my presentation.